The parameters we think are responsible in this question are the amount and viscosity of silicone oil, the aspect ratio and shape of the container, the powder size and ratio to oil, and the heating duration and initial temperature. Moving on, first we want to say the our heating method. We turn on the heater and waited for it to reach our desired temperature. Then we place the container on the heater and waited as the container gradually heated up. At the beginning, the velocity of the fluid is 0, and the initial temperature is equal to room temperature. When heating leads to convection, the fluid starts moving into perturbations in the temperature and velocity field, leading to convective Paris flow. Initially, as the fluid is heated from below, heat transfers to conduction, where thermal energy is transferred directly through molecular gradients. Once the temperature gradients become more pronounced, the convection takes the form front. The lower portions of the fluid being heated become less dense and begin to rise. As they ascend, cooler and denser fluid descends to replace them, creating a convective current. As the temperature and homogeneities increase, convective currents start emerging. Finally, these cells stabilize and create structured flow patterns, continuously shifting and merging. Now, we can categorize the phenomenon into three main stages: the initial heating and flow formation, pattern formation, and oscillation. Here you can see a video from our experiments that is not visible. Now, we'll be explaining this phenomenon in two modes: the thermal model and the flow model. We can define aspect ratio as a ratio of a container's internal diameter to fluid height. Now, let's move on to our thermal model. Increasing bottom temperature leads to the lower layers of fluid heating, decreasing the density of those layers and driving the hotter fluid up, while the fluid at the top descends to replace them. The resistive forces in this phenomenon are gravity, viscosity, flow turbulence, and heat propagation. Now, we can define the Rayleigh number as the ratio of buoyancy to viscosity forces multiplied by the ratio of momentum to thermal diffusivities. In essence, it quantifies the tendency for thermal convection to take place within a fluid. A critical threshold on 1708 indicates the onset of convection. Below this threshold, convection predominates and the fluid remains stable. When the Rayleigh number exceeds this critical value, the buoyancy forces surpass the viscous damping, leading to the onset of convection as thermal instability take hold. We can similarly define the Prandtl number as a ratio of momentum to thermal diffusivity, simplifying the tendency for convection to take place. Now, we're going to discuss the boundary conditions of this phenomenon. At the bottom of the container, we have uniform maximum pressure, which is represented by 1. At the top of the container, we have lower temperature, which is denoted by 0. The walls of the container have constant temperature for any given x. We can say that temperature in any point of the container could be quantified by this formula. Now, we model the temperature gradients using console. The bottom of the container is heated from below and has a uniform temperature distribution. The top of the container has a homogeneous temperature due to heat transfer of its surroundings, the air. And in this simulation, we are only simulating one convective current, not the entire container. And we can see that the fluid, hotter fluid rises from below, and colder fluid descends to replace it. Now, moving on to our experimental setup for the first part, we use a heater. We use a thermal vision camera. We obviously did use a mica powder in our experiments. Mica powder has a role in letting us basically see the cells better. On top of using mica powder in our silicone oil suspension, we also use a thermal camera to be able to better identify the temperature gradients in the system. Use a camera stand with a 90-degree angle to view the heater. We also use a thermal sensor using Arduino to better measure the surface temperature. Now, using the experimental data from the last experimental setup, we were able to get these points for the Rayleigh number over time. The horizontal line is the denoting the onset of convection, and this is our experimental observation. You can see differences between our experimental observation and the theoretical line. This might be due to several factors, such as the turbulences in the system or complications caused by nuclear powder. Now, by applying the fast Fourier transform to the graph of temperature over time, we are able to find the natural frequency of the system, being at about 0.16 Hz. The natural frequency of the system is the rate at which 1 grain of liquid powder cycles through the container. Now, we plotted this with Pepin Kaur. We can see other noises in the system, which might be due to liquid powder or temperature inconsistencies in the system. But the natural frequency is 0.16 Hz. Now, by using the same experimental setup, we were able to get this graph. The chart illustrates the relationship between surface temperature and time. All cases show the convection with the same temperature. Larger oil volume has a proportionally larger fluid height, meaning that it required a stronger convective current to cycle through the container and transfers heat at a lower pace. The 5 cases vary in heat transfer pace. Eventually, all containers match the temperature heated. The temperature of the heater, which is about 145, equals the temperature. This is due to the nature of convection. Now, here we have a graph for the peak temperature of fluid heating duration over time. We can see that it follows an exponential relationship, and it finally stabilizes as we reach the temperature of the heater. Now, we plotted the theoretical chart for temperature dependence of viscosity using the shown formula. We use this dependence in our Rayleigh number calculations because obviously viscosity is temperature dependent. The graph follows an exponential trend where viscosity decreases with an increase in temperature. Our experimental method for measuring the viscosity will be discussed later. Now, we tested different containers with different aspect ratios, and we can see a linear increase in peak surface temperature. This is due to the decrease in fluid height. Now, this graph compares the surface temperature profiles over time for 2 different shapes of containers, a cylindrical shape and a cube-shaped container. Convection is more efficient in cylindrical containers. Thus, the cylindrical container achieves higher temperatures. In a cube-shaped container, the convective current creates vortices in the sides of the container, wasting more energy, whereas the cylindrical container doesn't have sharp angles. Now, moving on to our flow model, we'll be taking account the forces that are being exerted on a small volume of the fluid, which will be represented by dV, which has a temperature of delta H and density of rho. Now, we can say that the 2 main forces on the system are buoyancy and weight, which we have represented by the following formula. By using this, we can say that the outward force being exerted on this volume of our fluid is the buoyancy minus the weight force. Using this, we are able to write this final equation for acceleration. Now, using this other formula for the dependence of density to temperature, we are able to reach this final equation for acceleration, which is alpha delta in the gravitational acceleration divided by v. Now, we obviously have to, this is the formula for the time it takes to complete 1 second. Now, we obviously need to take into account the viscosity, so we added terms to the equation taking account the effect of the liquid powder, and we reached this final equation for acceleration and time. Now, discussing the boundary conditions of this, we have no current in the walls, and the top and the bottom surfaces of the container have no velocity. The fluid rarely moves near the walls due to friction and the resistive forces. Now, here's a graph using the same theoretical formula for acceleration. Where we can see it, there is this experiment of acceleration over delta z. Here's a constant summation for the velocity field in one convective current. The lighter points in the simulation signify higher velocity. Due to the geometry of the system, an additional vortex will be created here, where we have the maximum velocity. The movement follows a circular pattern and has no velocity at the center. Now moving on to our experimental setup, we use the same heater, the stand, we use a flow meter sensor and a tachymeter, and we analyze the temp item. Now, for our verification, we have a comparison of our simulation and experimental results. As you can see, we use a thermal camera, and you can see that the results are like. Now moving on to our experimental method for measuring viscosity. To measure the viscosity of any fluid, we drop a metal ball with known density and diameter into a tall cylinder or bowl. We wait until the velocity of the ball reaches terminal velocity. Then by placing the input in the formula, we are able to find the viscosity of our oil. Now, let's move on to thixotropic fluids. Thixotropic fluids are when you insert shear stress to them, they decrease in viscosity. So we tested this and we found out that silicone oil is actually a thixotropic fluid. Here's the theoretical graph, and here's the experimental graph. Now, obviously, nickel powder plays an important part in the system, so we wanted to see the critical threshold for after which nickel powder will lead to chaotic systems, which we calculated using the Graphen experiment. Thank you.
Question time for the opponent.
Thank you for your presentation. We obviously put our effort into it. So, just two questions. On slide number 31, the last equation, does A not divide out on both sides?
Excuse me, can you repeat that question?
On slide 31, does A not divide out on both sides, or are they different variables there?
No, it's the same.
So, okay. And what conclusions can you draw from your experimentation? Like you could summarize it.
Okay. So we can say that viscosity is temperature dependent. As suction increases, there's an increase in the temperature difference in the system. We can see by our results that multiple parameters affect the convective velocity, such as the aspect ratio, shape of container.
Yeah. Did you do any experiments to ensure that your container was heated uniformly, or it just different?
Well, using the thermal camera, we could ensure that it was fairly consistent temperature readings in the container itself.
Okay. And on slide 7, did you state that the original velocity of the liquid was 0? In your explanation, I believe you said the initial velocity of the fluid was 0 before eating.
Yeah. Obviously, sorry, I can clarify that there is some motion in the fluid. Obviously, all fluids are moving continuously, but we're talking about bulk movement.
Okay. And did you investigate the type of satellite structures that formed, like the shapes and sizes?
Yes.
Okay. And on slide 17, could you quickly explain where this equation came from?
So is the time. Thank you. The reviewer, could you please write down the name on the board? Thank you. 좋아? 뭐 대충은 좋아. 빨리 해. 준이가 그래. So it's the time.
Okay, thank you. Once again, thank you for your presentation. I'm just going to start with an overview of the report. So the problem statement says uniformly and gently hit the bottom of the container containing a suspension of powdered oil and solid structures made for. Explain and investigate the phenomenon. Now, the report investigated many parameters such as the temperature, viscosity, shape, the volume of oil, and the initial temperature away. But we thought that the cell size and cell shape wasn't that clearly presented in the report itself, and we'd love to see a bit more about that. And then furthermore, an overview of the quantitative explanation. So, when the liquid is placed on the heating plate, the bottom of the low level of the fluid, its temperature is increased, and that will decrease its density. And because its density is lower, it will experience a force of buoyancy. And if that force of buoyancy is sufficiently above the resistive forces of viscosity and those, it will lead to the formation of some convective currents. And there are some boundaries. For example, it said edges of the container as that causes the flow to be zero when at that boundary line. And also the same thing at the top, as it was stated. We thought the quantitative explanation was very clear and we enjoyed it, but we thought that it may have been some parameters which weren't explained. So for quantitative explanation, it gave some formulas to calculate the buoyancy and weight of the cells, also some of the viscosity. It defined the Rayleigh number as like essentially an overview of the tendency for thermal convection to take place. It stated the critical value was about 1708, I believe that was based on literature, and it later did compare that to experimental results. So for the experimental setup, they had just a heater, thermal vision camera, a thermal sensor to measure the surface temperature, and they also measured the viscosity of the different oils using like for the job. We don't know if a single thermal sensor might have been able to be improved if you had to measure both the bottom and top. It will discuss that later. It found the natural frequency of the system to be 0.16 Hz, if I recall correctly. Larger oil values require stronger convective currents and take longer to heat. They gave some graphs of the theory and model of temperature viscosity changes, which we found matched quite well, and said that aspect ratio and fluid temperature correlated, like how fast is heated, and also that cylindrical containers is more effective than other shapes like squares, and we gave some theory and model summations with the acceleration. It also said that chaos arises at, I think, 800 ppm of micropowder, if I recall correctly. And as a just quick summary, we thought it was a very good presentation. We think the quantitative explanation was moderate, quantitative explanation also moderate. We think the results might actually be strong instead of moderate, and the experience setup was also decent. I would now like to invite the reporter for the discussion. ask a clarifying question. On slide number 17, could you just quickly explain where the equation came from?
So, what's your question?
Not sure I understand.
Yeah, here we find the boundary condition for our system. The root of theta, depending on x, y, and t, or the integral is 0. Meaning that at any
So-
given point, in the wall of our container, we have constant. That's basically what it means.
Yeah. I'm using theta to denote temperature, right? I can check.
Sorry?
I can check. Are you using theta as the temperature of the unit? Okay, never mind. Let me just move on. So you said you investigated the cell size and shape.
Yes, I was, didn't have time to cover that in our presentation, but here we have slide at the end. Yeah. Okay, so using Python, we use a simulation to graph the size of the cells over the velocity of the flow, right?
Yeah,
And so.
did you just model a single cell or like a bunch of cells in a container?
Well, here's the graph. So we have cell size over the velocity of the container, and you can see that it follows an exponential trend. Where the more velocity we have, the cell size is larger.
Okay. So
About,
why?
sorry.
Just positively, why would larger velocities lead to a larger cell size?
Right. So a larger velocity can be caused by different factors. For example, a higher temperature difference could lead to a higher velocity, or different aspect ratios, or whatever. So let's say you have a higher temperature difference, which causes a stronger, like
Yes, but if
more velocity.
if it's stronger like conductive current, wouldn't that be more unstable in a way? I don't know.
I don't agree with that statement. I believe that
Yes.
there's just it moves up the bulk of the
Yeah.
so it moves up the high velocity. We need to
Yeah.
greater sizes. Yeah.
Also with shapes of the cells, they appear to be hexagonal in shape mostly. Do you know
We
why?
also investigated that. We know that the shape here. I don't know what happened in the PowerPoint, but we had an explanation that the shape of the cells follows a Voronoi diagram. So do you know what a Voronoi diagram is?
No, just very briefly.
Right. So if you have a plane and we basically divide the plane into some areas by defining some points. So we have a plane, we have some points, and we divide the area of the
So-
plane into some segments
Yeah.
based on the closest point to those segments.
So I don't get.
That's just sorry to interrupt you. That follows. You can say that the cell sizes, the cells follow a Voronoi diagram.
Okay, so I believe the shape has like optimized some parameters then. So do you know what it optimizes this shape?
Okay, yeah. So hexagonal shapes optimize the energy.
So the shape just minimizes the energy in the system in a way.
Not the energy waste. Yeah, the hexagonal shapes. Could I elaborate further?
Yeah.
Yeah, sure. Do you have a marker?
And it's not.
Thank you. So as I mentioned that if you have a plane and you define some points on it, a Voronoi diagram basically what it does is it sort of like divides the plane into some segments based on they're like
Okay.
especially from those points, right?
Yeah.
So what this does is it actually minimizes the waste of energy because, basically what happens is the convective current rises from below and it moves to the walls of the cell, right?
Okay,
So,
so-
let's say each of these is a cell and
Yeah,
then
so-
goes down, right?
Yeah.
It goes with me.
But-
Right. So basically what happens is this minimizes the
Okay, so okay, I'm not sure I still quite understand why exactly Hexagon would do that. But with the cell size also, is it just like a ratio between the amount of convective currents and the velocity that convective currents need to travel to like minimize the energy waste, or how to define the cell size quantitatively?
Here, by cell size, we mean like the area of the cell. It's
Yeah,
centimeters
but like-
power 2. Yeah, the 2 is
But what are the main parameters that like cause the cell size, the specific cell size?
right. All the parameters that we mentioned in our presentation can affect the cell size, right? But we didn't graph any of them singularly. Instead, we used the velocity of the
Yeah.
fluid.
But can I explain like qualitatively why velocity leads to larger cell sizes?
Right. So more velocity means a stronger convective current. Right. Here's it.
Okay. Are there limits to this assumption? Like, are there some like velocities that don't cause cell scission, like too turbulent or?
So obviously, if the velocity is too low, we wouldn't have like cells forming. We would just have like a very mild convective pattern that wouldn't reach the surface of the fluid, right? But if you have insanely high velocities, I'm actually not sure. I would like to know your input on the question.
Personally, I think if convective currents become like too fast, it would lead to some amount of turbulence forming, which
Right.
might disturb the cells and might not be cells at all.
I believe
Um,
that. Could I answer your question? I believe that the system would enter like a chaotic state. So instead of like a uniform, like
Yeah, I see.
cells forming, we
Yeah.
would have like this sort of
Yeah, I understand what you
it's
mean.
like the
It's
oil is
you-
stirring.
Yeah. You didn't measure the like where that value could be, right?
No.
Okay.
So I
Fine.
believe it's the real number is above 10 to the power of 4. So
Yeah.
if the real number is
Yeah,
above
yeah,
that
yeah,
number,
okay.
yeah.
Okay. Lastly, like not lastly, but as you can see with a micropowder, like the areas between the cells, it looks like the micropowder is more concentrated there. Do you know why? It's like, if I'm correct, micropowder is just used to like indicate the convective currents in a way.
Right.
So where the currents go down, like where it's denser, the micropowder is also more concentrated there. Do you know why?
You can say that. But we know that the fluid rises at the middle. We can also
Yeah.
see more liquid powder in the actual middle of the cell, where
Yeah.
the fluid rises, and also at the wall of the cell. So I would presume it's because maybe there's when you're looking at it from above, we see more concentration in that area. So we think there's more micropowder there
Yeah, but
because it's right. Can I draw something? Yeah. So let's say that this is the cell, and we're looking at it from the side view, right?
Yeah.
So we know that the fluid rises
yeah.
from below and then goes down the sides, right? So we see more fluid micropowder concentration in this area and on the walls. This is what because when we're looking at it from above, there's a lot of micropowder moving in this. This is like the current looks like this.
I'm quite sure if I agree with that, because like, in my view, the micropowder was homogeneous, like, in the mixture.
Yeah, obviously
So-
at the beginning it was homogeneous,
Yeah,
but
but-
as the convective currents start forming,
Yeah, but I don't think like movement of different parts of convective current should change the concentration of micropowder. But
I'm just saying it looks more concentrated when
So-
you're looking at it from above.
so you're saying that it looks more concentrated, but it isn't.
There is actually more liquid powder in this like
Okay.
vertical cylinder, but like than here. That is due to the because we have no velocity here,
Yeah.
so there's like very few liquid powder segments.
Okay, I'm sure if I agree, but let's just move on. You measured the Lyapunov experiment on one of the data slides. So, could you just give us how exactly you measured the chaos in the system?
Yeah, I know what's going on. Okay.
Quickly.
Right. So this is the formula for the different
So is this parts per million of the micropowder? The PDA.
We wanted to see the threshold after which when we add the liquid powder, the system would like exhibit behaviors.
Okay, so what does the ppm represent?
ppm is it's right here. Yeah. ppm. I think we're all- mass of the nitro powder to the mass of our entire suspension in 10 to the power of 6 kilograms. Oh, kilograms. Yeah. So this is the ppm, the definition of ppm. So the amount of the powder, the mass of the amount of the cooling system plays a part. Is obviously using powder for indication, like so we can clearly
Oh,
see.
so it's the time. Sorry. Thank you. So, Johanan, please give your summary.
Yeah. So I think we had a pretty good discussion. We talked about some of the more qualitative reasons behind the cells forming, like why the micropowder would indicate the cells so clearly, and cell sizes, cell shapes, why hexagons are the most efficient. I don't think we got a satisfactory answer for everything, but there was a lot that helped. And then we also had a lot of other questions, like with the Lyapunov experiment. Unfortunately, we didn't get to finish that, and I think we clarified more of the parameters that we investigated with the cell size, which we didn't see in the presentation, but we did later see. And yeah, overall, I think it was a pretty productive discussion, and thank you for the reporter.
Thank you. And question from the reviewer.
Reporter, do cells change in time?
Yes.
So after what time did you measure the cell size?
Like when I started measuring the cell size.
You said that they change in time, so after what time did you measure their size?
After 1800 seconds.
Okay, thank you. Opponent, do you think that does the mica powder affect the flow?
According to the last graph, it seems like it does. I don't know why, but
Okay, thank you. Reporter, is the critical Rayleigh number for which the convection occurs same for every fluid?
I believe so.
Okay, opponent, do you agree?
no.
Okay, thank you. Could you show me slide number 24? Okay, so is it the theory or the experiment?
This is the experiment.
Okay, thank you. Opponent, do you think that the chaos occurs as the reporter said?
Chaos.
Yes.
Yeah.
Okay, thank you. Could you show me slide number 40? With the experiment also done. Okay, so in the meantime, I would like to ask if you kept the upper part of the fluid at the constant temperature.
Well, obviously, as convection occurs, the whole fluid is getting warmer, so it's increasing in temperature.
Okay, thank you. So what was the role of the tachometer? Slide number 40.
It was used to verify. So first we used it for philometer. We used a philometer. We know that omega equals omega equals R times V. So we use the philometer to measure this velocity to find omega, and then we confirmed this omega we found using the philometer. And
Okay, thank you. Could you show me slide 46? Is it the theoretical prediction from your flow simulation or just the fit?
the blue line is the
Yeah.
theoretical simulation.
Okay, thank you. Opponent, do you think that the container diameter is relevant?
Yeah, it is, because the boundary conditions will handle that.
Okay, thank you. Were the both containers you used the same volume?
Which both containers?
You used a circular and a square
They
container.
had the same aspect ratio.
Okay, so they did not have the same volume. So
Sorry,
opponent,
time's out. Thank you. What is the time?
Welcome, ladies and gentlemen. My name is Błażej Gorzołek. I'm representing Poland, and I will be reviewing problem 10, Rayleigh-Bernstein convection. What I liked about the report was that the reporter identified the important parameters for the phenomena such as the gradient of temperature, the viscosity, and the container size. She identified both methods that the heat can be transferred in this phenomenon, which are convection and heat diffusion, and she said that the density difference is the reason why the flow is upward. She also identified that there is a critical threshold for the Rayleigh number after which the convection occurs. She used a thermal camera to accurately map the temperature, and she studied the size of the cells, which is important as the problem content asks us about the cells. However, what I think that was a bit poor investigated was that she did not investigate other aspects of the cells, such as their number and the shape. She also used an open container with heating walls, so she did not have a lot of control of the temperature of the upper part of the container, which is important as in order to calculate the Rayleigh number we need the temperature difference between two sides of the fluid. She also did not compare the aspect ratio of the container to fluid parameters. And what I especially didn't like about the report was that she did not give us any qualitative energy analysis, which I think is important as the system uses this energy transportation method that is most energy efficient. So when the convection is more energy efficient, it uses convection, and when the heat diffusion is more energy efficient, it uses heat diffusion. And so she did not explain why there is no convection for a low temperature difference. What I liked about the opponent was that she asked if the container was uniformly heated, which I think is important, as this is what the problem content states. She also asked about the theoretical boundary condition, and she mentioned the stability of this stability analysis of the cells, which I think is important as the cells can change in size, and the stability is important as for the cells are stable for higher Rayleigh numbers. She asked about, however, what I didn't like about the opponent was that she did not talk about how poorly the temperature was controlled, as the upper part of the container was not kept at the constant temperature, and she did not talk about the heating motion of the fluid before the cells form. She stated some opinions. What I liked was that the size and the shape of the cells should be more investigated, as those are important for this phenomenon, and the problem content asked about this. What I didn't like about the opinions of the opponent was that he stated that it can influence the existence of the flow of in the phenomenon, and I think that the mica powder is too light to actually influence the flow. In the discussion they talked about the simulation, and I think that the reporter should model more cells than just one in their simulation. They also talked about size of the cells, and I think that there are many things that can influence their size, and it should be more investigated. And they also talked about about convection velocity, and I think that at higher temperature difference the convection would be faster as there is more buoyancy, and I think this should be more investigated. What I did not like about the opposition and the report was that there was no energy analysis, which heat transport method is the most
Sir,
efficient.
it's the time. Thank you. So the reporter, please give your summary.
So in my analysis, I only analyzed the relation between the size of cells and the velocity. I believe that several parameters affect this relation. However, like the aspect ratio, the temperature difference, I only tracked the relation between cell size and velocity. Now, he also mentioned I didn't have I used like saran wrap and like sort of like plastic to for the walls of the container to do not allow for any temperature difference conduction with the environment. However, at the surface of the fluid, obviously it is in contact with the room. It is doing thermal conduction with the air. I don't believe that is a parameter to be controlled to keep the surface temperature constant, because we will be disrupting the system. In my console, I only simulated one conductive current, and I used that data to I had a good characteristic difference. So I do not believe it is necessary to provide a simulation for the entire container. The opponent also asked me about the reviewer also asked me about the difference of the onset of conversion with different fluids. I do not believe that the onset of conversion changes with different fluids. I also believe that the number of cells has a backwards relation with the size of cells. So I believe that is why in my analysis with the size cell, we also can provide an explanation for number of cells.
Thank you. Now, question from the jurors. Question, please. Question?
Yeah, one question for the reporter and the opponent. Do you think that you can really explain cell formation with buoyancy and weight only? If I saw, well, there was equation for buoyancy and weight, and also for you.
I don't think it would be complete with my other parameters like viscosity, and I think the main aspect of self-formation is like the energy minimization. So I don't think it could be explained just with those two, but I'm not sure.
So could I answer that? I believe that each cell is numerous conductive currents that are happening in sort of a donut shape. So we could we're analyzing only one conductive current when writing that equation.
Okay, thank you.
Thank you. Any more questions?
I can maybe ask the reviewer. So, just state yes or no if. So, for the phenomenon to occur, does the top of the container, the temperature of the top of the container, need to be constant?
It doesn't, but I think it would be good to keep it constant for the experiments.
Okay.
Question for the reporter. Can you show me the slide when you model the convective cell? That you show the boundary conditions. Yeah.
Do you want the console solution?
No. The slide that you show that you stated the boundary conditions. Yeah.
Do you mean the prior slide or the?
I think the before one.
Okay.
No, under the flow model, not the thermal model. Under the flow model. Yeah. So why do you say that the vertical velocity is 0?
There's velocity right at the walls is 0. I don't mean that the entire velocity is 0, just at the walls.
You mean the walls of the cell or the walls of the container?
Wall of the container.
Okay.
So friction and turbulence.
Okay, thank you. For the reporter, how does the size of the powder affect the cell deformation? What do you think?
I think that the powder does not affect cell formation per se. However, changing the properties of the powder can affect the chaos in the system. So I believe if you use larger grains of the powder, that could affect perhaps it would need more it will have more energy. It will have more rates, so it would make perhaps more noise in the system. Yeah, exponential results.
Reviewer, do you agree?
I think that Mika Powder has a very a low effect on the phenomenon because it's very low and it stays at the top and the flow is occurring in the entire container. And I think that the role of the Mika Powder is just to mark where the cells are.
Okay, thank you. Any more questions? Please.
Okay, so there is a graph on the cell size versus velocity of fluid, right? How do you measure the velocity of the fluid?
I think it's 46.
Experimentally, we use cell profiler. We also use different methods. Some of them work, some of them don't. First, we try tracking a grain of powder when it moves throughout the cell, and like I try to use that data. That didn't work out. We use, I think at least we use a cell profiler to track the velocity of the system. We also tried using the plunger to track the velocity.
Okay, thank you. Now, Joros, please do the grading. mass of the reporter is 5, 4, 4, 4, and 3. And the gradient of the opponent is 5, 5, 5, 4, and 3. And for the reviewer, it's 6, 6, 7, 7, and 5. Okay, let's give some comments. And may I have first question? For the reporter, we have single low score from teacher.
Yeah, what to say, it's partial data, 1.25 and 1. From the experimental point of view, I would like to say it's a good start. Good experimental start but the problem is not finished. Problem is cell formations, and I would like to see the end of this experiment, analyzing cell formations, dependence of B, dependence of height, and so on and so on. From theoretical point of view, I'm not sure that these, let's say, theoretical graphs are from relevant theory. I think it's not possible to explain these phenomena only with force to mechanical force, buoyancy, and weight. So, that's it. I'm sorry, but yeah.
For me, I give a 5 for the reporter because the survey analysis is quite clear, and then comes to simulation your phenomena to support the investigation. Also, it's some lack of the experimental parameters to investigate. So actually, the partial model is 1 plus 1.5, 2.5. So that is 5. And for the opponent, we have 3, also from Christian, please. For the opponent?
For the opponent, yeah, continuing or looking the reporter and the report of this project, I think you as opponent missed to see, let's say, solution of the problem in law. Your partial points are 0.5, just ask a few questions about specific, but not about, I think, so relevant. And your speech was, let's say, a little bit cool, because you just on one side noticed notes from the reporter, and your comments on the right side are so altered to just 1 or 2 comments, and so on. In discussion a little bit better, but in total 3.
Thank you. We have quite similar. We have 3, 5. Maybe you please give some comments.
Okay, my partial grade for the question asked is somewhere between 0.5 to 0.75. And my partial grade for the opposition is 1 and half. And the discussion is 1 and half. Okay, I think that your review basically is not bad. It's quite okay. But in the evaluation, I think for some part you didn't really put your evaluation. So it looks like you don't have any comments on what they are doing. Okay, and for the discussion, I think to the note I took is like you didn't hit the point of the key of this problem, because this problem certainly the flow up concerns with the buoyancy, flow down concerns with stronger gravity. But in between, when it flows horizontally, there should be something extra, right? Otherwise, it can flow down anywhere. Okay, so this part they didn't mention, so I think that will become your job. Try to pick it up. Okay, like what you know is it's certainly concerned to the heat transfer. Okay, so because of this, I think that the only mark I can give is like this, and your major point, grabbing point is about the question you asked and the review.
Thank you. And for the reviewer, we have a single 5. Again, question.
Again, yeah. This morning, very strong, yeah. Yeah, it's, let's say, average overview of what's going on here, but I think for a good review, you have to stress in general task fulfillment and what's going on in theory, what's going on in experiment and so on. I saw details, but not, let's say, a picture, is it a good experiment, missing points, self-formation, and so in global, your view of, in general, this problem.
Thank you. We have 2, 7, maybe Maros,
Yeah,
and
okay.
some comments.
Yeah, so I actually ended at 6.5. I just decided to round it up. But yeah, I partially agree with here my colleague is Kresho that maybe you could focus more on the task fulfillment, but what brought it up for me is the fact that you had very good time management, because I have seen many reviews where the time management was bad, and this was not your case. What I also like that you brought some own opinion, which maybe the opposition was lacking, so maybe that's why I graded it a bit higher. And yeah, maybe you could get some more points if the prioritization was a bit better, because I don't know, I think you focus too much on like keeping the top temperature constant and stuff like that. But I generally liked it.
Thank you. So we should end this stage, and we will have a 10 minutes rest and come back. Thank you.